Looks like I've got a bunch of submissions for the reservoir sizing. I'll be interested to look that over and make sure that you've got the correctly sized reservoir. The next thing that's on your agenda as far as submissions is a homework assignment due on Friday. And there are two main things in that homework assignment. One has to do with chokes, and so meaning the steps that we've talked about before and what we're going to go over today, enlargement, contractions. And then the other part of homework 10 has to do with weirs, and we'll be talking about weirs on Wednesday. And so if you get to a weird problem in the homework assignment, then you may want to wait until after Wednesday to attempt that one. All right. So here we have a nice photo of a beautiful mountain river. You can see the snowy peaks off in the distance. That might be West Virginia, but it's not. But it could be. It's up in Alaska. And the interesting thing to look at is the flow as it goes around these piers. And so the piers are actually effectively changing the cross-sectional area of the stream, because we have some stream width, and then where the piers are in place, essentially that is reducing the available width of the channel. The flow has to go around that obstruction, and so now the channel is less wide at the piers. And so in a case like this, the question arises, what will be the behavior at the obstruction? Will the water level rise or will it fall at the constriction itself? Now we know from the discussion of choking that if we made it too narrow, then it would cause the water to get deeper upstream. It would cause a choke. But even before choking, there can be a response at the place where the change is made. So we have location 1 upstream, location 2 downstream. This section where the flow is contracted is location 2. So what's happening there at the constriction? Will the water level rise or fall? Well, we can't predict unless we do some calculations first. This isn't something where we can just apply a rule of thumb and say, if you make the channel narrower, the water gets deeper. If you make the channel wider, the water gets shallower. It's not that simple. We have to analyze the flow regime, among other things. So let's just go through some definitions to begin with. Remember that a constriction is when you can have a step up, or the channel bottom raises. We've talked about this kind of constriction already. When a constriction happens like a step from a previous lecture, what occurs is that the flow per unit width, lowercase q, remember, is big Q divided by B. And having a step up doesn't change either of those things. It doesn't change the big Q, the flow rate. It doesn't change the width of the channel. And so flow per unit width, lowercase q, stays the same, but the E decreases. The specific energy after the step, here at section 2, the specific energy is less because of the step. So E1 plus, E1 equals E2 plus the delta Z. And so the E at 2 is less than it was at 1. If the width of the channel decreases, however, that's another kind of constriction that we haven't really investigated in a lot of detail. So like the previous picture, the width of the channel decreases because of some sort of an obstruction. Then the flow per unit width is increasing this time. Previously, when it came to a constriction that was a step up, neither the Q nor the B changed. But here, the flow per unit width increases because B, which is in the denominator, gets smaller. And the energy level is the same. And so consider a channel. This is depicting a natural channel where you have water flowing through a wide river, and it's moving slowly. But then as the channel gets narrower, the velocity obviously is going to increase because it's required to increase in order to maintain continuity. But our question is, what we're going to try and talk about today is what happens to the flow depth? Does it get deeper or shallower because of that constriction? So the behavior that we're going to be looking at is governed by what's happening upstream of the constriction. And the energy equation will allow us to compare two sections, and we're going to also use the Froude number to diagnose what's the flow regime. Remember that previously we said if conditions upstream were subcritical, then downstream they're also going to be subcritical, and it helps us to know which of the two positive roots in a cubic equation we should select. And we're going to do the same thing here. We're going to solve cubic equations, and we're going to analyze the flow regime upstream in order to know which of the two downstream depths we ought to pick. So subcritical upstream will be subcritical downstream, and the same is true with supercritical. If we diagnose the flow regime upstream of a constriction, then find it supercritical, it'll be supercritical downstream at the constriction as well. Any questions so far? Well, let's take, for example, putting in a pier, as was depicted in that nice mountain picture of Alaska. If we put in a pier, we have some original channel. In this case, the channel width is 2.5 meters, and we have a certain flow rate, 2.25 cubic meters per second, and a known flow depth to begin with at 1. And then downstream of that, a bridge is being built over the channel, and so we have to put in supports. And those piers, since they go through the stream, are effectively decreasing the available flow width for the channel. And so we want to go through and find out what is the water depth at the constriction. And to do that, we're going to step through, first of all, finding the velocity at 1, finding the specific energy at 1, and then finally we'll be able to find the depth at 2. Okay, so we know that the energy at 1, the specific energy at 1 is going to equal the specific energy at 2. And we can write the energy in terms of just y1 plus v1 squared divided by 2g is equal to y2 plus v2 squared divided by 2g. The critical depth formula, we saw that in the quiz today. For a rectangular channel, let's find the critical depth here. It'll allow us to know whether the flow at 1 is supercritical or subcritical. So the flow per unit width is 2.25 cubic meters per second divided by the channel width of 2.5 meters. And we're going to square that divided by 9.81 meters per second squared and take all of that to the 1/3 power. So the critical depth is 0.436 meters. Since y1 is greater than yc, conditions are what in terms of the flow regime? If the depth at 1 is deeper than the critical depth, does that make it supercritical or subcritical? That's right, subcritical. Okay, so we'll file that away in the back of our minds. We'll find the velocity at 1. Velocity at 1 is just going to be q divided by a1. So that's 1 cubic, 2.25 cubic meters per second divided by 2.5 meters wide and 0.9 meters depth. So the velocity at 1 is 1 meter per second. And it becomes easy to find E1 now. E1 is just going to be the depth, which is 0.9 meters plus velocity head, 1 meter per second squared divided by 2 times 9.81 meters per second squared. So the energy at 1 is 0.951 meters. That's the specific energy at 1. Okay. Since we don't know the velocity at 2, we'll make that substitution that we often do for the velocity head term. Instead of having v squared divided by 2g, we'll say q squared divided by 2ga squared. And so we are going to say 0.951, which is the energy at 1, is equal to y2 plus q squared divided by 2ga2 squared. All right. So that is y2, the unknown depth, plus 2.25 cubic meters per second squared to 9.81 meters per second squared. And then the depth is going to be 2y2 squared. At 2, since each one of these supports are 0.25 meters wide, they're circular supports. So what is the new flow width at cross-section 2? There's the overall 2.5 meters, but we have to subtract the width of the piers. And so the actual flow width is 2 meters. And so here where I'm saying E1 is equal to E2, the area, that's the flow area at location 2, is going to be 2, so that's referring to the width. And y, of course, is the depth at 2. So there's a new flow width. The flow rate didn't change. Q, big Q, is still the same, but B2 is different. Okay. So this becomes 0.951 is equal to y2 plus 0.06451 divided by y2 squared. All right. And that we can say is 0.951 y2 squared is equal to y2 cubed plus 0.06451. And we can rearrange that further. y2 cubed minus 0.951 y2 squared plus 0.06451 is equal to 0. And then we go through the process of finding the roots for that. There are going to be 3 roots. The negative root, which we immediately reject because we know that the flow depth won't be negative. And then there's a supercritical root of 0.3197 meters of depth and a subcritical root of 0.865 meters of depth. And we select the subcritical root because the flow regime at 1 prior to the constriction was subcritical, and so now it will be subcritical again. So it's actually the water's going to get shallower, and that's contrary to what we maybe would have as a gut reaction, right? I mean, the gut reaction says that, you know, someone who's not considering it from the context of specific energy might think that if you put in some sort of a constriction, if you're blocking the flow, well, then that ought to make the flow deeper, but it doesn't. The flow gets shallow. The velocity is going to increase, and so it's the specific energy that governs the depth. It's not continuity equation that governs the depth. We could find the velocity at 2. Now that we know the depth, then we could find V2. You know, V2 is just going to be Q divided by A2. We have all the information we need to find V2, but it's not continuity that is the reason why it got shallower. It's the other way around. It got shallower because of the governing principles of specific energy, and because it got shallower, the velocity increased. Now, everything we've just done assumes that there's no energy loss because of the constriction. And sometimes that's not true, and the energy loss needs to be accounted for. And always that's not true. Sometimes it's important enough to account for the energy loss that we'll make an effort to do so. And we're going to talk about that later today. But just to point out that so far this solution was assuming that there is no energy loss between 1 and 2 because of the constriction. All right, questions before we move on? Simple, right? Just solving a cubic equation, really. All right. Here's another kind of contraction. So the first kind of contraction we talked about is what if piers are put into a channel? The channel itself isn't getting any narrower. Well, what if the channel does get narrower? Okay, so conceptually what we're saying here is that the flow rate Q stays the same. We can have steady flow. We can have steady flow where conditions, the flow rate's not changing over time. And in fact, the flow rate isn't changing with respect to position. Other things are, but Q isn't changing with respect to position. Velocity is changing with respect to position. Flow per unit width is changing with respect to position. But flow rate itself, Q, is constant from between 1 and 2. But when you make the channel narrower, B decreases. And so what impact does that have on flow per unit width? Will it get bigger or smaller when B decreases? Flow per unit width, lowercase q. It gets bigger. Okay, so a small b gives you a big lowercase q. So that increases. By making the channel narrower, you're packing more flow per unit width. Each meter of width in the channel is carrying more water than it did before. So lowercase q gets bigger. What about the critical depth? What's going to happen to the critical depth at 2 compared to the critical depth that it used to have at 1? Okay, so if flow per unit width gets bigger, so will the critical depth. It will increase as well because we've got a bigger Q. G stays the same. The equation stays the same. It's still rectangular between 1 and 2, so this equation still applies. And so now we've got a bigger critical depth because the channel got narrower. And so if we wanted to express the situation as a specific energy diagram, which is always a good idea, even if it's not to scale, it's always going to be helpful for you to just draw this curve. And it's amazing how often just drawing the curve and the axes will stimulate, oh yeah, that's right, minimum specific energy corresponds to the critical depth. Right? That's something that doesn't immediately jump to mind otherwise. Just sketching out that curve can remind you of the principles. And so here we have 2 curves. We've got the curve at 1, and so this is the original specific energy diagram. But when we make the channel narrower, since we are increasing the critical depth, we've got a higher critical depth than before. That shifts the specific energy diagram up and to the right because both of these things increased. The critical depth gets bigger. That means that the minimum specific energy gets bigger. Because remember, E minimum is just 3/2 y sub c. And so a bigger flow per unit width gives us a bigger critical depth. And a bigger critical depth also gives a larger specific energy. And so this is the specific energy diagram at 1. And this is the specific energy diagram at 2. All right. It's always good to graph the diagrams, but this actually tells us something useful about the last example that we just worked. Okay. The question on the last example was what? We were trying to find out what at 2. What behavior change were we trying to find at location 2? The new depth. So can these 2 diagrams give us an idea of what the new depth was? Are they able to answer the question, what will the new depth be? If we assume the specific energy doesn't change, no energy loss, Ryan, how does this tell us the new depth?
Well, if you know it's subcritical, then it's going to be lower.
Okay, we've got 2 crossings, and if we know it's the subcritical crossing, this was curve 1, And we know that curve 2 is going to be above and to the right. So we draw some hypothetical curve 2. And we don't even have to have it to scale, but we just know if this curve 2 has to be offset above and to the right, then this was our original depth, y1. The new depth, y2, is going to be shallower. And so qualitatively, by sketching out these two curves, we can just get a sense for what should be the answer before we actually solve it numerically. You know, when we solve it numerically, we find out that y1 is equal to 0.9, which is greater than y2, which was 0.865. Well, if before we did that, we just sketched the curve and we say, all right, it should be shallower than it was before. Here's the diagram, it should be shallower. Then we have that available as a confirmation once we do the calculations later on. So it's important to go through these steps. I mean, what's the sequence, the logic sequence? The first thing that we did is B smaller leads to Q bigger, which leads to Y sub C bigger, which leads to E minimum bigger. Okay, and so all of that, therefore, shifts E curve right, because there's more minimum energy. So that's how we know it's shifted to the right. And Y sub C bigger, that's how we know that curve 2 is shifted up. So that's why the curve is to the right and up, curve 2.
Yeah, why is the depth of 2 lower, but the critical depth higher?
Critical depth is higher because there's more flow per unit width. And the depth is lower because, I guess we could say, more of the energy is as velocity head than as depth. You know, remember that all of that specific energy exists in two places. It's a combination of depth energy and velocity head energy. And so the reason why at 2 it's lower is just there's more velocity head energy than there was previously. I don't really know that that's an answer so much as me just restating the equations, but that's what governs it, is the principles of specific energy. All right, so let's take a look at a contraction. We've got an example with a contraction here. We want to know how far can we push this? What is the minimum width for B2 before choking occurs? How narrow can that channel be? All right, and so we know B1, Y1, V1. We can use that to find E1. The specific energy at 1 is going to be Y1 plus V1 squared divided by 2G. So how much specific energy is there at 1? 5B plus 3B per second squared divided by 2G. 5.140 feet of specific energy at 1. All right, so a principle to keep in mind is the smallest B, that's what we're asking about. The smallest B will lead to the biggest Q for some given flow rate. So we're looking for at 2, the smallest flow per unit width. What we're going to say is, what do we know right before choking occurs? What is the flow condition right before choking occurs? You know, it goes subcritical, a little less subcritical, getting closer and closer to critical flow. But right at that incipient point where choking just about to occur, conditions are critical. And so what that tells us is that we're going to let E minimum at 2 equal this 5.140 feet. So we're going to keep making location 2 narrower and narrower and narrower right until the flow depth is critical there. And it's minimum conditions. And so the minimum condition means that the total energy is going to be the 5.140 feet, and at minimum energy, critical depth. And so YC is 2/3 of E minimum. So that is 2/3 of 5.140 feet. That means that the depth, the flow depth, is going to be 3.427 feet. So by definition, the minimum channel width is going to be when the conditions just barely go critical at 2. And when they barely go critical, this is the depth that we'll have. Any questions so far? Well, how much of that then is, remember that E is y plus b squared divided by 2g. What we're saying is that 5.140 is equal to 3.427 plus b squared divided by 2g. So we can find the velocity when conditions are critical. The velocity at 2 is going to be 10.50 feet per second. And that's one way to find it. The other way to find it is that we know that, well, maybe we can't find it another way yet. Not yet. We can confirm it later. So in minimum energy, 2/3 of the energy is as flow depth, 1/3 of it is as velocity head. So we found the velocity, and for a Q of 150 CFS, then the area at 2 will be Q divided by velocity at 2. Okay, the area 14.28 square feet, and the therefore B2 is A2 divided by Y2. We know that the area is 14.28 square feet. And we know that the depth will be the critical depth of 3.427 feet. And so we want to find what is the width. 14.28 feet. And the 3.427 feet. 4.17 feet, and any narrower what happens if we made the channel even narrower than that? Choking would occur. And what would that mean? Specifically, if choking happens, then what occurs during choking? That's right. The water depth would start to get bigger upstream. It would cause the water to accumulate upstream until there was enough energy to make it through the obstruction. So what was the process here? Like, what's the problem-solving procedure? We found the specific energy at 1, and then again, there's that big idea that critical conditions are what corresponds to minimum energy. And so if we're trying to find the minimum width at D2, any narrower than that is going to cause choking. And so right before choking, it's critical conditions. And so we invoked this idea that at minimum energy is the critical depth. And that's how we then were able to find out what the depth was, the velocity, and then apply that to continuity equation. All right, as I mentioned, these contractions and expansions can actually cause energy loss between the two sections. And some typical values that are cited in your text is that a contraction can have a C value of between 0.1 and 0.6. And the C value is multiplied by the velocity head. And that's very similar to what happened with local losses in pipe flow. Remember, in local losses, what we had was K, some K value multiplied by the velocity head. And that's what accounted for energy losses due to like an expansion, for example, or a valve, or a change in direction. When it came to pipe flow, we'd have KV squared divided by 2G. That's how we accounted for energy losses. We do the same thing here. The specific energy at 1 is equal to the specific energy at 2 plus the loss between them. And so the loss is on the right-hand side of the equation, same as it was in closed conduit flow, because between 1 and 2, when the flow is going from 1 towards 2, that means there's going to be less energy remaining at 2 because of the energy that's lost. And here is that this form of velocity head was written on your quiz as well. You know, sometimes velocity head we say is v squared divided by 2g. Sometimes we say velocity head is q squared divided by 2ga squared. And now here on screen what we're saying is it's flow per unit width squared divided by 2g depth squared. So if we divided this by b, then we get that. Because q divided by b gives us lowercase q. A divided by b just gives us the depth. Okay, so this is how we can account for the losses. In this case, we've got an expansion. We just finished talking about a contraction and how that shifts the specific energy diagram. I'd like you to go through the logic and try and figure out, if you make the channel wider, how is that going to change the specific energy diagram? The same sort of step-by-step logic of considering the flow per unit width, consider the critical depth, consider E minimum. What will the new specific energy diagram look like? Sketch that down on your page. An expansion means that B increases. And if B increases, then flow per unit width decreases. And if flow per unit width decreases, then Y sub C is smaller. And if Y sub C gets smaller, then so does the minimum specific energy. Okay, so if Y sub C gets smaller, then that means that Y sub C2 will be lower, like down, on the curve. And that means E minimum 2 will be to the left on the curve. And so this is 1, and 2. Okay, here was our E minimum 1, and this is E minimum 2. And that was Y sub C1. And here is Y sub C2. So that's how it shifts the curve, opposite of what happens during a contraction. Don't just leave it to a guess, though. Step through the logic and prove to yourself why it shifted to the left and down.
We're now going to consider an example where there's a rectangular channel that is expanding from a starting width of 3 meters to a finishing width of 5.7 meters. We know that the flow rate is 9.9 cubic meters per second, and the depth at 1 is given as 2.75 meters, and through the transition there is an energy loss, and the coefficient for that energy loss is 0.45. And so thus what we're trying to find out is what will be the depth downstream of this expansion in view of the fact that the specific energy equation says that there has to be a new flow depth because of the new flow per unit width and also because of the energy loss.
In this example, we're going to consider the case of a channel that is expanding. The original cross-sectional width of the channel is 3 meters, and it expands to a width of 5.7 meters. And through the transition, we are given that there is a coefficient of loss of 0.45. The initial flow depth is 2.75 meters. The flow rate is 9.9 cubic meters per second. And so essentially what we're trying to find out is what is the new flow depth downstream because of this transition. First of all, for the flow rate of 9.9 cubic meters per second, we can find the flow per unit width at 1 is 9.9 cubic meters per second divided by the 3 meter channel width, and that is 3.3 meters squared per second as the flow per unit width at 1. And we know that for a rectangular channel, the critical depth can be found by squaring the flow per unit width divided by g to the 1/3 power. And so that is 3.3 meters squared per second squared divided by 9.81 meters per second squared to the 1/3 power. If we put that into a calculator, we'll find that the critical depth at section 1 is 1.035 meters. And so we have to analyze the flow regime at 1, and since y1 is greater than yc, then that means the upstream flow is subcritical. In other words, we knew that the initial depth was 2.75 meters, and since the critical depth at 1 is less than that, conditions are subcritical upstream at section 1. Alright, now if we substitute it into the specific energy equation where the conditions at 1 are equal to the conditions at 2 plus the loss, what we have is that y1 plus q1 squared divided by 2g y1 squared is equal to y2 plus q2 squared divided by 2g y2 squared plus c q squared divided by 2g y2 squared. What we're going to do is substitute all of the information that we've got, and the only unknown here is going to be the depth at 2. Okay, and so for this case, the flow depth at 1 is 2.75 meters. The flow per unit width, 3.3 meters squared per second. Squaring that. 2G. And the initial flow depth, 2.75 meters squared. That's equal to the unknown y2 plus the flow per unit width at 2. When the channel is going to be expanding, the new flow per unit width, so lowercase q2 is going to be the same 9.9 cubic meters per second divided by 5.7 meters, and so that flow per unit width is going to be 1.737 meters squared per second. So 1.737 meters squared per second, squaring that to 9.81 meters per second squared, and the unknown y2 squared, plus the c value, which we're given, the losses are 0.45 times 1.737 meters squared per second, squaring that, divided by 2 times 9.81 meters per second squared, and again y2 squared. If we combine everything together, we'll get 2.823 is equal to y2 plus 0.223 divided by y2 squared. And we can rewrite that y2 cubed minus 2.823 y2 squared plus 0.223 is equal to 0. And putting that into a solver, finding that the three roots are negative 0.269, 297, and 2.794 meters. This depth is the supercritical root. We had subcritical conditions though, and so this is going to be the new downstream depth when we do account for the energy loss. And so the depth at 2 will be 2.794 meters, and this does account for the losses in the transition.